Hello, everybody. So, today we are going to start our new chapter, which is chapter number 30, Quantum Physics. And it's a very interesting chapter in which you will actually know how the basics of quantum theories actually got developed. Even a concept of literally light is so much complex and it has so much in it. This is the beauty of quantum physics. So today we are going to study about light. Yeah, we all know what is light. If I ask you that what actually is light, whether it's a particle or it's a wave, so it's a very complex question. So let's discuss it today, and we'll come up to one conclusion, which is the first outcome of our lesson, that we need to appreciate the particular nature of electromagnetic radiation, and we are going to evaluate that whether or light is a wave or it's a particle. See, you can actually see that light is I hope you guys remember young modulus experiment, the double slit experiment. Yeah, if you remember that, then the life will be very easy today. Now let's see about that. What actually is light? So the most beautiful aspect of light is the laser light till now. Okay, and how you actually create a laser light is that you just arrange the particles in one particular direction, and this makes your light in a very high intensity light, only focusing in one direction. And we know that a lot of medical treatments are now given by using this laser lights and stuff. If we talk about that, whether how we can model or particular light in terms of or particle, or whether we think it's a wave. Now there are many scientists who talk differently about light, that whether it's a particle or it's a wave. Let's discuss every theory which is behind it. If you just want to model a big particle, let's say, yeah, if you want to model up some big particles, it's very easy. You can use a macroscope, or you can just use your own eyes to see. Like for example, you're playing billiard and there are like many balls like here, yeah, and if one of the particle actually or one of the ball hits the triangle, all the balls will get dispersed. Yeah, and we say that the small particles are going to move and jump here and there. Okay. Now, if you want to use a small microscope, yeah, and you want to see the nature of gas molecules, which is over here, yeah. So you need a microscope, and you will see that how if you bombard a particular particle on another particle, how it is going to behave, what will be the path, how haphazardly it is going to follow a path. Okay. Now coming back to our next page, which is this one. Okay. Now, if you see from this one, if we are modeling any particle, what we see in that particular particle, yeah, we see that what is the pressure, what is the temperature of that particular gas. We also talk about the radioactivity of that particular element. We also talk about the chemical reaction when we are talking about particles. These all are the properties which we actually discuss when we are talking about particles. Yeah, that whether it's electricity and we are talking about flow of charges, we say okay, we are the macroscopic phenomena we are considering is current which is forming, right? Then the gases, if we talk about, so we say we talk about its kinetic energy. But what is the phenomena that is occurring, that because of that kinetic energy we can measure the temperature, the pressure is changing because of that energy. Yeah, and you can see this particular table to see how you can actually model particles in science. Okay. Now, if we talk about the wave model, let's see how you can actually model a wave. If you see the waves and you go to Cornish and you see waves, have you ever seen a sine wave there? But whenever we talk about waves in physics, we always draw a wave like this, right? But in reality, the wave is not like this. Yeah, we model the wave like this. Okay, we say that it's like it's a transfer of energy is going on and on and on, and it's going up and down. So it is replicating the motion of the waves which you see on the sea. Okay, but actually this we call it as it's a simple wave. But if you see the waves of ocean or sea, you those waves are very complex waves. They are made up of many different type of sine waves. So that's why you cannot exactly replicate that. But when we want to model a single wave, so modeling it through sine wave is the easiest job. All right. Now, if you remember the Young slit experiment, yeah, I hope you guys remember. It was like, let me draw on this one. Yeah, it was like that you have a slit, and then, yeah, and you are passing a beam of light here, and then it is going to split like this, and when it is going to pass through these two lights, so it will be like this. Yeah, and then you will see some dark and some bright fringes over here. So when you are modeling it as if you want to model a wave, what factors you should keep in mind? Yeah, it's refraction, reflection, interference. Okay, these are the things which you should keep in mind when you are talking about waves. Yeah, and what you need to think about when you are talking about particles. This is a very good paragraph. Okay, since particle models can also explain reflection and reflection, it is diffraction and interference that we regard as defining the characteristics of a waves. Okay, because if particles can also reflect them, they are actually bombarded on each other and they are changing their paths and stuff. So reflection and refraction is actually happening there as well. But diffraction and interference don't happen in particles. This is a major characteristic of a wave. Okay, so wave do not have a charge, or wave do not have a mass like the particle have. Wave is a behavior, it's a phenomenon. Okay, and how the wave actually tells you about diffraction and interference. Okay, so this is the basic model difference between, you can say, your wave and particle. Now let's talk about light, and let's see that what people say about light and how the different theories are actually formed. Now let's say that light is a wave or a particle. Let's discuss, like, it started with particle as light as a particle. Newton said it first that light is actually a particle, and he also said that this particular, it has all the phenomena of what a particle have, that when you bombard one wave light into another wave light, the particles moves, and stuff like this. So for a long time, Newton's view was actually prevailed, and nobody questioned him that is it correct or is it wrong. He used the explanation, both reflection and refraction, in his book Optics, that your particles can actually refract and it can actually reflect, and he proved it through different experiments that yes, it is happening, so it's a particle. He also said that your light actually travels faster in water than in air. Okay, this was by Newton in the book Optics. It's written that the light travels faster in water as compared to air. So there was another scientist called as Thomas Young, and he showed that the light can actually diffract and it can interfere, as he done the experiment as Young double slit experiment, in which he proves that light actually can diffract and it can interfere as well. Now all the physicists at that time, they just thought that Newton knows the best, so they never questioned Newton, and they said that no, Newton is correct and he is not wrong. Then another scientist, which is Leon, he experimented and he said that no, the light travels slower in water as compared to air. So over there, the contradiction actually happened, and it was proven experimentally. So the Newton theory was, a bit late behind, and now people were more focusing that light actually travels as in the form of a wave when it's in space. Okay. Now, other scientists were also curious, and they experimented what Newton did. They were more focused on the Newton's theory, and they really wanted to prove that yes, it's a form of a particle, and it's a wave, but it's also a particle. So there was one more. There was one more theory. Okay. So one of the scientists, what he actually did was, if you guys remember this Geiger counter, I hope from grade 10, that you guys remember that how to detect like the gamma rays and stuff, you know, the EM wave was bombarded to some particle, and then there was a counter over here, and this is the Geiger counter, and it is used to count each and every particle, or each and every gamma ray which is getting detected, each and every particle of gamma ray, and it will keep on adding up the counter. Yeah. So what he did was he bombarded again, and the gamma rays are actually produced, and gamma rays are, we all know, part of the electromagnetic spectrum. Okay. And they are actually from the same family as that of your visible light, but actually it is of far more higher intensity, or you can say far more high energy. So the wave actually, if something is getting counted, so we say that that particular thing is discrete, and it's not in the form of a complete wave. We say that it's discrete. So if discrete things are there, so it is more likely to be a particle. Okay. Since when he passed the gamma rays, he was able to count by using the Geiger counter, and he counted. So they say that okay, uh, this is happening and it's a particle. But the effect is more obvious with gamma rays because they are more energetic as compared to the visible light spectrum. All right. Now the next is photons, very popular thingy. Now Einstein came into action, and he said that he will also prove something. So now Einstein explained the photoelectric effect, that what actually is a photoelectric effect. And he came up with the idea that yes, Newton is correct. The light actually travels in the forms of packet, and those packets he named as photons, whereas the Newton called that as corpuscle. And he said that these photons are the packet of energy, and it travels, and they have the properties of a particle. Okay. And then he actually used the Planck's theory, which is this one, that E is actually equals to HF. He said E is equals to HF, and H is actually the Planck's constant, which is 6.63 into 10 raised to the power minus 34. What he evaluated from here is that if you have a high frequency, like high frequency gamma radiation, so it means that a high energy photon is going to be produced. Okay, if you have a very high energy, then you will get a very high frequency as well. Then he further the Einstein actually related your lambda, the wavelength, with your energy, and he said that if the wavelength is very long, your energy will be very small. This is the reason that the gamma rays, they have like shorter wavelength, because they have a high frequency, so they will have a shorter wavelength. So because of this, they are more energetic as compared to the visible light spectrum. Okay. So now your homework is, and I will grade that as a quiz. Okay. These questions, question number 1 and 2, you need to solve it and submit me by tomorrow, and I will grade that as a quiz. Thank you so much.